the relative advantage and disadvantage of the two main colliders, proton antiproton and electron positron collider. The proton we have seen is made out of 3 quarks held together with a bunch of gluons. Okay. So in proton antiproton collision, you can study quark antiquark collision and probe the same physics as in electron positron collider, except that you have to pay a price in terms of the beam energy, because a quark carries on the average 1/6 of the proton energy momentum. You see, the proton energy momentum is shared half and half between the gluons and the quark, and because there are 3 quarks, each one on the average carries 1/6 of the proton energy. Okay, so the interaction energy will be smaller than the center of mass P bar P energy, whereas electron position, the entire electron position energy goes into interaction energy. Okay, so to have the same interaction energy S prime, the proton antiproton center of mass energy must be 6 times larger compared to the electron position center. Clear? It turns out that it is a very small price to pay because of the enormously higher synchrotron radiation loss in the electron positron machine, because the amount of synchrotron radiation loss per turn goes directly as the 4th power of the beam energy and inversely as the 4th power of particle mass. Because of the smaller electron mass, you have an enormous amount of synchrotron radiation loss, which means not only gross wastage of energy but also radiation loss. Okay. To keep it under control, you have to increase rho, which is the radius of the ring, but then of course the construction cost of magnet, everything goes up. Again, one can make a real life comparison. Look at 2 machines, both built at CERN, to study the production of Z boson. Z boson mass we have seen is 90J, but let's call it 100J, round it off. Okay. So the P bar P collider had to have a 6 times larger center of mass energy, 600J, that is the factor of 6. The LEP one had a center of mass energy of 100J. Okay? But the radius of LEP one was 5 km against just 1 km per P bar P collider. And the cost of LEP one was $1 billion against only 300 million for P bar P. Again, out of the 300, 200 had already gone into the proton synchrotron, which is existing. With just $100 million extra, it could be converted into a collider, okay, and produce the boson Z boson. In fact, when Rubia got the Nobel Prize in 84, or 84, it was said that he got Nobel Prize not so much for discovering W boson, whose existence was not in doubt, because there are already indirect signs of existence of W boson by that time. But providing a simple and quick method, cheap and quick method of producing W boson, because the success of an antiproton-proton collider was not clear at that time. In fact, the trial was shared with Van der Meer. Van der Meer proved the technology of focusing on the antiproton. Okay, so you see that to probe the same energy range, the P bar P collider has an enormous advantage in terms of cost benefit. Okay, the corresponding advantage of the electron positron machine is one of precision. You can tune electron positron energy to be at the rest mass energy of the Z boson you want to produce. Okay, you can tune proton antiproton center of mass energy, but you cannot tune the quark antiquark center of mass energy, okay, because their energy is always distributed. Okay? So that means in an electron positron collider, you can have much higher rate and a better mass resolution. In fact, in LEP one produced something like 1 million Z boson events per year, compared to only a few dozen at the CERN P bar P collider. Besides, electron positron signals are clean, while proton antiproton signals are dirty because you have to live with this with the spectator quarks and gluons. They are not taking part in the desired interaction, but they are always there at the underlying unit. Okay? So any experimental structure have to contain in the underlying unit. Okay? So the advantage of this was making a precision study of Z boson physics, which enabled you to make precision study of weak interaction quantum correction, which gave Nobel Prize to Taube and Feldman. Okay? So Taube and Feldman got Nobel Prize for LEP, just like Higgs got Nobel Prize for LHC. The experimental didn't get it. Okay. So you see the complementarity between the two kinds of machine. So the lesson you learn from this slide is if you want to probe a new energy range, a higher energy range, you first do it with a hadron collider, P-Barkey collider, PV collider. Okay? Because it is cheaper, but if you find something interesting, like Z boson informed, okay, then you follow it up with an electron precision collider for the precision study. Clear? And this principle has guided the history of colliders from its beginning. This slide gives you a list of past, present and proposed colliders. The first was the sphere collider at Stanford, electron position collider with center of mass energy of something like 6J. The physics highlight was discovery of charm, quark and tau leptons, both of which got from there. Then came Doris machine at Hamburg and Caesar at Cornell, center of mass energy of something like 10J, which physics highlight was detailed study of the body. You see, the invariant energy of this Stanford collider was equivalent to that of the invariant energy of the fixed target proton synchrotron at Brookhaven National Lab. In fact, charm quark was simultaneously discovered at both these machines. That's why both Richter and team shared the Nobel Prize. Likewise, the center of mass energy of center of momentum energy of these machines were comparable to that of the fixed target Fermi Lab machine. The first indication of bottom quark came from Upsilon discovery of Fermi Lab. But the detailed study of bottom quark was possible only at this interesting okay. Then that shows you the complementary between the directions. Then came the Stanford machine PEP and Hamburg machine Petra, jacking up the energy to something like 40J. The physics highlight was the study of gluon attractor. Then came the Tristan machine at Japan, pushing it up to 60J. Nothing much came out of that, but the main thing came from the CERN P-Barkey collider, 600J center of mass energy, which effectively made 100J, and that was enough to produce W boson and Z boson because they are mass less than 100J. Next came the Tevatron machine at Fermi Lab. Okay, it is a P-Barkey machine with a 2000 J center of mass energy. If you take out the factor of 6 we mentioned before, then 2000 divided by 6 will be 350 J, which was enough to pair produce top quark because each top is 125. The next machines bridged the gap between the reach of the P-Barkey and electron position collider. They increased the electron position collider energy to 100J to make a precision study of Z boson, Stanford linear collider and CERN LEP 1, 100J. And then LEP 1 was pushed up to 200J, that is LEP 2. That enabled them to pair produce W boson. W is a charged particle, so in equivalent collider for stars conservation you have to produce them in pair. Okay, so they could make a precision study of W and Z physics and precision study of the weak interaction quantum correction. Hera machine at Hamburg is a different kind of machine. You remember from the very first slide that electron-proton collision, you study the quark substructure of proton with an electron. Now by increasing the energy to a collider, okay, you made a precision study of the quark substructure of proton. This is not a new particle study kind of machine. It's a precision study of the quark substructure. The new particle study kind of machine is the Large Hadron Collider with a center of mass energy of 14 TeV. It is in the same tunnel as Artlet, so the radius is 5 km. But even if you take out the factor of 6, you still get an effective center of mass energy of 2 TeV, 2000 J, which is an order of magnitude more than the level. And the physics highlight is the Higgs boson discovery and the ongoing search for bosons. Okay? And at some future date, we hope to probe this 1 TeV kind of energy range with an electron-positron collider. We do not know where and when, but we have a name. It is called International Linear Collider. It has to be a linear collider because the synchrotron radiation velocity is so huge for this energy range that you cannot have electron-positron circular collider. So it has to be linear collider, and it has to be international because no single country or continent can afford the cost. Okay. When I was showing one doesn't know when I was showing this at an international conference, one experimentalist came to me and said, "Sir, why you have been so pessimistic about linear collider?" I said, "Why?" He said, "You could have given 2 0 and 2 question marks. Why 3 question marks?" Okay. I shall discuss Higgs physics in the next class, and Suji will be discussed at length by Amitabh. What I will do in the remaining half an hour or so is to discuss this new particle signal. You see, these are unstable particles. When you produce, they instantly decay. Nonetheless, they leave characteristics imprint on their decay product from where you know that there is the signal coming body. So I shall discuss this. Okay, let's look at electron-positron collider producing pair of charged quark, tau lepton or bottom quark. So this is the Feynman diagram, except that now because of the space constraint I have put time axis as the horizontal axis, space as the vertical axis. So electron positron through a virtual photon goes into a charged quark pair, tau lepton pair or bottom quark pair, and these are the spatial pictures in the event plane. E plus E minus going to back charged quark pair, back to back tau lepton pair, and back to back bottom quark pair. They have to back to back for momentum. Okay. The typical lifetime is in the range of picosecond, and since these are relativistic particles, velocity is velocity of light, so the typical range of this particle decay is few hundred micron. Now, thanks to the development in silicon chips technology, this few hundred micron is enough to reconstruct their path before their decay. So from the event you can reconstruct the path before the decay, and you know that such unstable particle has been produced from the track they leave in the outcome. Okay. Gluon is slightly different story. What happened? This is the Feynman diagram. Electron positron through a virtual photon goes into light quark pair of quark pair of quark and antiquark. Occasionally one of them will radiate a gluon, just like an accelerated electron radiates a photon, Bremsstrahlung photon, that will be a Bremsstrahlung photon. So instead of a 2-body final state, you will see the 3-body final state, and when you see the 3-body final state, and you see their energy distribution, angular distribution, rate, and you can compare with QCD prediction, and you see from that comparison you know that it's not object. Now, these objects come as jets. What are these jets? You see, I told you that the quarks and gluons are perpetually confined inside a hadronic dimension of 1. So how do they come out? Okay. The answer is very simple. It again comes from quantum mechanics, because quantum mechanics tells you that vacuum is not empty. Okay, vacuum is containing umpteen amount of quarks and gluons, thanks to the uncertainty principle, which provides the rest mass energy and kinetic energy. Okay, so each of the produced quark and gluon, which is energetic, carrying some 10-15 J kind of energy, can pick up additional quarks from this vacuum and come out as colorless cluster of hadrons, mostly pions. Okay? These appear as 3 jet. Again, the reason is very simple. We saw that they will carry the energy and momentum of the produced quark antiquark gluon. There will be only limited momentum smearing across those directions, because that has to come from the momentum carried by the vacuum quarks. But we saw the size is 1 Fermi. So the momentum of this vacuum quark will be inverse of 1 Fermi, which is 200 MeV, 0.2 GeV. Okay? So there will be only limited momentum smearing, otherwise they will come out of the thin jets. And the energy and momentum of these thin jets are the energy momentum of the quarks and the quarks and gluon produced. And from the QCD theory potential, we know this is R. You see, discovery of W and Z boson is a different story, because they are so massive that they decay at the moment of their creation. Nonetheless, they leave unmistakable imprint on their decay product. Again, the point is very simple. What is happening when you produce a Z boson? There is an enormous energy momentum carried by the constituent up quark, down quark of the proton and antiquark of the antiproton. They are colliding they are fusing to convert their kinetic energy into the rest mass energy of the Z boson. You see, once that has happened, once the kinetic energy is converted into the rest mass energy, the sense of the initial direction is lost. When it decays, it doesn't have to decay in the longitudinal direction in the vacuum pipe. Okay, they can decay quite often in the transport direction. So you will see a electron positron pair or a muon pair carrying a huge transverse momentum of 45 J, half the rest mass energy. And they are so clean that if you see one event, you know that it has to be there. So by the time of discovery, there were maybe 4 or 5 events.